identified 10 symmetry operations. And these are point operations. So what is the meaning of a point operation? All of these operations intersect at a point. So if I take any lattice point, then these point operations pass through that lattice point, through any lattice point. So these are point operations. And what are the point operations? They are 1, 2, 3, 4. We do not have a 5-4 rotation in solids. In molecules we may, because there is no restraint in a molecule. A molecule can have 5-4 symmetry, but not a solid. 6. And then we have 1 bar, which is an inversion about a point. We have 2 bar, which is the same as a mirror operation. So this is a plane, but and we also have in Goto inversions. So we have 3 bar, 4 bar, and 6 bar. So each one of these inversion operations is an operation followed by a rotation followed by the inversion. So these 10 point operations exist inside solids, and these point operations determine the macroscopic symmetry of crystal. How does the crystal look like from the outside? And if you take the geometric center of that crystal and perform a point operation, a group of point operations corresponding to the point group to which that crystal belongs, the external morphology of the crystal will remain unchanged. So these are the 10 point operations, and they all come in combinations. So you have a lattice or a structure, they come in combinations, incompatible, mutually compatible combinations to give you 32 groups. Those 32 groups are called point groups. And there are 32 of these. The point groups determine the macroscopic properties of the crystal, they determine the macroscopic appearance of the crystal. So now let's develop these 32 point groups and see how these symmetry elements combine together, lump together into these 32 classes and form these mathematically distinct groups. Okay, so today's lecture, lecture number 2, is going to focus on the development of point groups. So we try to do this pretty systematically. Okay, so what's the simplest symmetry operation? Just do nothing, 1. Okay? So if a lattice or a crystal structure may have this trivial symmetry, the basic symmetry element is do nothing. So you can have a crystal that is totally asymmetric, which means the only way in which it can be rendered invariant is by rotating it through 360 degrees about its geometric center. For a lattice, you take any lattice point, and the only symmetry element that renders this lattice invariant is by doing nothing. So that is a group, and that group comprises just one element, which is identity. Okay, so if I were to represent, so group number 1 is simply do nothing group. Okay, and it has symmetry element, which is the identity operation, just the identity operation. And if I want to represent this, I can draw a circle. And now what I'm trying to do is drawing a stereographic projection or a stereo diagram. Just for my convenience, I draw a line in between and it creates an object. So, if only one such object exists inside this plane, inside this stereogram, this diagrammatically represents the point group 1. Okay? This is just the basic symmetry element and the most basic of the 32 point groups. Okay? Let's proceed. Let's now proceed to another point group. So now I will first draw the stereogram. Starts off like this. And if I place an object here, and I have a twofold axis of rotation, remember only point operations are allowed, which are one of those 10 operations. A twofold axis passes through the center of this stereogram, which means there is a 180 degree rotation from this point. Then this point is transformed here. A point that is above the plane remains above the plane. Point that is below the plane remains below the plane. Okay? So this is the next point group, which is denoted by 2. So the symmetry operation is a twofold axis rotation. It's not quite for the point group is also denoted by 2. Keep that in mind. So the point group symbol is 2, and the symmetry operation is also denoted by 2. So this is the international notation, the HN notation. In the old notation, this would be called C2. This point group would be called C2. In the old notation, this point group would be called C1. So if this was a group, a mathematical group, how many elements would be in this group? 2. What are those elements? Identity and the twofold rotation. So this group has order 2, which means it has 2 symmetry elements. And luckily one of those symmetry elements has been denoted by this green symbol. Okay? And the cyclic group. Then you can have other cyclic groups as well. So now we develop 2 point groups. Let's do the next one, which is a threefold rotation. Okay, so if I have an object here, this object lands here after a 120 degree rotation, and then you do another 120 degree rotation. On this object it lands here. This object lands here. So this group now has 3 elements: identity, it has a threefold rotation, and a threefold rotation done twice. Okay, so this group is given the symbol 3 because really there is a threefold axis of rotation here. In the old rotation, this is called C3, and it has 3 elements. The elements in this group are 1, threefold rotation, and threefold rotation done twice, right? So it's a threefold group, but the point group itself is labeled as 3. Okay, so let's do the next one. So now we have identified 1, 2, 3 point groups out of the 32. Now these point groups describe crystals, real crystals. These point groups describe lattices. Okay? The arrangement of atoms inside a crystal or the arrangement of points inside the lattice, they're all describable by one of the 32 point groups. And remember I'm talking about continuous space filling solids, not molecules, standalone molecules. Molecules, the number of symmetry elements in groups could be higher. For example, a linear molecule like ethylene, C2H2, that does not fall into one of these categories. Okay. Buckyball, C60, a molecule, has icosahedral symmetry. That does not fall into one of the regular three-dimensional solids. So molecular symmetry has more symmetry elements. So let's look at the next group, and you correctly guessed this would be this would involve a four-fold axis of rotation. You draw a line here, object here, right? So this is 4, old symbol C4, and it has 4 elements: identity, 4 squares, 4 cube. So all of these are cyclic groups. And I can draw yet another cyclic group, which has 6-4 symmetry. Okay. This is an object, this is a lattice or a group with 6-4 symmetry. There is a 6-4 axis of rotation here at the center. This is our 5th point group. Denoted by the symbol 6 in the old rotation C6. Okay? And it will have 6 elements in it. So now we've kind of done with the the first 5 point groups. These are the 2-fold axis of rotation, 3-fold axis of rotation, 4-fold axis of rotation, 6-fold axis of rotation, nothing else. Okay? Now, these 32 point groups we'll learn in the next class can also be classified, subdivided into other groups, into other kind of groups. So you lump all the point groups that have a 4-4 axis of symmetry, and they will form another unit or another collection of point groups called the tetragonal crystal class, the cubic crystal class, the orthorhombic crystal class. That will learn later. Yes, please.
Yeah, 6-5 tetragon.
Sorry?
Like 1, 6, 6 square, 6 cube, 6, 4, and 6, 5, 6, 7, 8, 2.
So now what we would like to do is, to these point groups, cyclic point groups, let's add a mirror plane. Let's go to the next level of investigation. Right? So, if I consider this, and I add a mirror plane, suppose the mirror plane is horizontal. Then what's going to happen? This object that is above a plane will be reflected below the plane. That's the only thing that's going to happen. So I can represent this on a stereogram. I draw a circle. This object is above and it coincides, when looking from the top, it coincides with its mirror image. And the mirror image has to be an antimer of the original. The mirror image of the original, just like the two hands, they are mirror images of one another, but they cannot be superimposed onto one another. So if I take my two hands, so if I take this one hand and put a mirror plane, I will get this hand. But there is no way in which I can superimpose my two hands together. Right? So if I just turn this around with 180 degrees, my thumb is that if I put my hands like this, then this thumb connected to this thumb, this this middle finger connected to this middle finger, and like all of these fingers, if I connect these by straight lines, they will join at a point. So this hand is the diameter of this hand. Like a D glucose molecule is an diameter of an L glucose molecule. An L amino acid is an diameter of a D amino acid, and so on. Right? So mirror images are connected through this an antimorphic operation, and I need to represent this somehow. So the crystallographer's convention is that I break this object into two parts. If one is above the plane, I put a plus sign. The other has to be below the plane, I put a negative sign, and I put a comma here. So this is a symbolic representation of a group that has a horizontal middle plane. And that group is given the symbol 1 bar. Oh, sorry, it's not 1 bar, it's middle plane. It's given the symbol M. Sorry. It's given the symbol M.
M is a point group.
M is a point group. M is the symbol of this point group. In the old notation, I think this is called sigma H, or horizontal middle plane. So the only symmetry element this group has is a middle plane in the plane of this diagram. Correct? By the way, this point group M, is this also equal to a two-fold rotation followed by an inversion operation? So if I look at this two-fold operation, this is a two-fold operation. This object comes here, but then if I invert this object about this point, I'll get an entire one at the exact same location. So this M is really equal to 2 bar. Okay. So this point group M can also be represented as 2 bar. Alright. So middle operation equal to 2 bar. So now I have my 6 point groups. Let's look at a simple inversion. Object here, inverted about this point. This object, if it's above the plane, here it's below the plane, and since it's an inversion operation, I need to add a comma here. This is another point group. This point group has a symbol 1 bar. Simple inversion. I think it has the same symbol in the old notation as well. Okay, so this is my 7th point group. Okay, so the action, in fact, let me, this point group is a simple inversion operation. In the old notation, I think it's denoted as S1. S1. S stands for an improper rotation, which is a rotation that involves an inversion or a rotor inversion. Okay, so I've added a mirror operation to this. I get this. What if I add a mirror operation here? I can also add a mirror operation here. Remember that this simple mirror operation on 1 gives me 2 bar. Okay, keep that in mind. So let's have a mirror operation here onto this point. I'm going to successively add a mirror operation here, 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 and here. Okay? Quick question, Subramani?
वन को हम किस प्लेन में मिरर प्लेन कहेंगे? वन बार का सॉरी.
One bar to go mirror image नहीं है. Because this is not a mirror image. This is an inversion operation. This one does not have a mirror plane. This one does have a mirror plane. Okay? So this is obtained by concatenating a one-fold operation with a mirror. Okay, just one mirror. This has a symbol M. This group has two elements. It has an identity operation and M. This group has two elements, identity operation and one bar. Now let's add the mirror operation to this point group. So this is my original point group, the 2-point group or C2 point group. If we draw bigger circles, slightly bigger circles. Now, mirror image of these points, something that is above will give me an object that is below with a comma. Right? So these two objects that are above the plane, when transformed by the mirror, they will give me an anti below the plane. So each one is split into two. Remember, this is just a diagrammatic representation. Okay? So this group is formed by a mirror operation onto 2, and it has a symbol 2. There's a 2-fold axis of rotation, which is this one, because it was there in the original cyclic point group. But now we have a mirror plane that is perpendicular to this 2-fold axis of rotation. Correct? So put an M as well to it. However, since the mirror plane is perpendicular to the proper axis of rotation, to the principal axis of rotation, the crystallographer's convention is to put a forward slash. So it's 2/M. This is the symbol of this point group. And in the old rotation, it's a C2 operation followed by a horizontal mirror plane, so it's called C2H. Okay. So this is my 8th point group. You can add more. Let's add a mirror plane here. Oh, let's add a mirror plane here. Okay, very simple.
So all of these are going below the plane basically.
So one point is above. The mirror plane puts that point below the plane. Anything that is below goes up. That's why I need to put a positive and a negative sign here. I didn't put a positive and negative sign here because it's assumed that all these objects are above or below. So now for this particular case, I start off here. So I need to first of all create these points on the horizontal. So each point above gives me a comma below. Plus, minus, plus, minus, plus, minus, right? Got it? Now the symbol for this image, in the international notation is not 3/M. Rather, it is 6 bar. Because it's the same effect if you did a 6-fold rotation. Instead of rotating this original point with the plus sign by 120 degree, you rotate it by 60 degree and then take an inversion about here, you'll get this comma with the negative sign. And you can test this for all of these points. So this 6 bar is the same as doing a 3-fold rotation and a mirror plane that is horizontal. The symbol that is given to this point group is 6 bar. The old symbol, nevertheless, is C3H, the Schwann-Fleiss notation. Okay, so this was my 9th group. Out. So this is 4. There's a 4-fold axis of rotation here. And a mirror plane that is normal to this. So let me check. Yes. A mirror plane normal to the principal axis of rotation 4/m. Old symbol is C4H. Alright? The 11th group is formed by adding a mirror plane here. Okay, and this is 6, and symbol for this is 6/n C6H. So now we have created these groups C and H. The group C and H in the old notation, they have really been created by taking CH group and concatenating it with identity or a mirror plane. So this is how we have constructed these groups. The original cyclic groups followed by the either doing nothing or adding a mirror plane. So the cyclic groups are a subgroup of the C and H group. So now we have identified 11 point groups. Any questions? This mirror plane was actually in the horizontal plane, as far as our diagram is concerned. But the mirror plane, you could also have a mirror plane along the vertical axis. So you take the original cyclic groups, C1, C2, C3, C4, C6, take these 5 groups and add a mirror plane that is vertical.
So vertical से आपको इससे out of the page.
Out of the page. So in all of these diagrams, the mirror plane is in the page, in the blackboard. And I can represent, if I were to represent this by an element, generally you put at the top left this sign, which represents the mirror plane that is in the plane. Right? This sign. Just to identify that the mirror plane is in here. Okay? Is in the plane. G.
So can you draw the mirror plane for one figure कि मतलब हम reflections ले कहाँ रहे हैं and actual object कहाँ है mirror कहाँ है because वो सारा mix up हो रहा है.
Mix up or what?
चलो if you can just visualize for one figure where is the mirror plane? And
This blackboard, so for this figure, the mirror plane is the blackboard. So if I look at this, so let's keep it, let's look here, okay, simple. So if I look from the side, So how am I drawing the diagram? If I look at this image from the side, what I have is, this is my mirror plane. I have an object here above the mirror plane. When I take the image inside the mirror plane, the image in the mirror plane, I get the same object here, I get a reflection here. So this is above, this is below, so I put a plus sign here and a minus sign here. So this has to be the diagonal of this, so I put a comma in here. Now when I look at this thing from the top, I have no way of drawing two circles from the top because they are totally coincident with one another. So I just draw this one circle. So from the top, that image in blue is drawn like this. इसका ये मतलब it's not the same object, there are two objects. but मैं कैसे बनाऊँ? दो ऑब्जेक्ट्स मैंने बनाने हों, कैसे बना? एक तरीका ये कि मैं एक ऑब्जेक्ट ये बनाऊँ, ये प्लस है, दूसरा ऑब्जेक्ट भी इसी के ऊपर से देखूंगा तो कोइंसिडेंट हो गया। तो मैं एक तो तरीका ये कि मैं ऐसे दिखा दूँ इसको, लेकिन फिर मैंने कॉमा भी तो दिखाना ना, एक में तो कॉमा भी है, तो उसको दिखाने का एक कॉम्पैक्ट तरीका ये है कि मैं एक ही सर्कल बनाऊँ तो दोनों हिस्सों में डिवाइड कर दूँ, एक के साथ प्लस लिख दूँ, के साथ माइनस लिख दूँ, और एक जिसमें माइनस लिखता है उसमें कॉमा डाल दूँ। तो ये तरीका है इस चीज को दिखाने के लिए, ठीक है? So in all of these point groups that I have drawn, the mirror plane is in the plane of the paper, in the plane of the blackboard. I could also draw the mirror plane in the vertical direction. So what the mirror plane, the plane of the paper is doing is that it's converting a plus to a minus and making an diamond as well. Now I'll give you an example of what if the mirror plane is vertical. So if in this example, let's, do you have questions, Alice? If it's pressing.
वही पूछ रहा था कि वर्टिकल के लिए इज इट लेफ्ट टू राइट और टॉप टू बॉटम?
कुछ भी हो सकता है, दोनों हो सकता है, कुछ भी हो सकता है, एक ही बात है, भी देखते हैं. So if in this case you draw a mirror plane, so this is my C2 axis. I want to add a vertical mirror plane to this. So I don't want to disturb this diagram because this serves as a visual treat at least to me. So let me redraw this and add a vertical mirror plane here. Request. So this is my C2. Now instead of a horizontal plane, suppose I add a vertical plane. That vertical plane is now along this axis. So the vertical plane is coming out. Now what will be the image of this object? Where will it lie? On the other side here, something above remains above. Something below remains below. Like this. So this is the stereogram for this new point group. Now this new mirror plane is, the axis of rotation is also vertical, it's coming out, the two-fold axis of rotation, and the mirror plane is parallel to it. In fact, axis of rotation lies in the mirror plane. Correct? So the symbol for this is 2. Okay, so what should be the symbol for this? 2. Just give a guess. This is a mirror plane M. But instead of writing forward slash M, we just write 2M. Okay? But the symbol for this really is not 2M, it's 2MM. Why is that? So how many mirror planes exist in this figure? 2. So here is the first one, where is the second one? This is one mirror plane here.
One mirror plane, but the mirror twice.
No, there are two mirror planes. There is one mirror plane, and then this mirror plane has automatically generated another mirror plane. So one symmetry operation on a particular group can generate another symmetry operation. This one mirror operation has generated a new mirror operation. So now we have two mirror planes that are mutually orthogonal to one another, and both of them are vertical. So the symbol for this point group is actually 2mm. Yes, please.
That is not an environment.
Oh, sorry, it is an environment. So it's an environment. This is environment of this. So, yes. This is an environment. But all four are positive. Right? So this is the symbol, and the short presentation, this symbol is C2V. V stands for vertical. Okay, got it? So likewise, we can create C3V, C4V, C6V. Remember that adding one symmetry operation can generate its own symmetry, other symmetry operations. For example, here a 4-4 axis of symmetry generates 4 square, 4 cube. Here one mirror operation on C2 generates another mirror plane. Okay. So the elements in this group, will be all the elements here which are identity and a 2-4 relation, C2, followed by 1 and a mirror plane that is vertical. So let's put this the prime sign, M prime. Okay, so all the operations will be formed from this configuration. So likewise, I can have C3V. C3V is, if I put a mirror plane over here, let me first draw C3. This is C3. If this were my mirror plane. So now your question is, someone asked you a question, which direction the mirror plane should be applied. So you applied it one and you got it automatically in the other. So in this case, if I were to draw, if this were my vertical mirror plane, this object would come here, this object would come here, this object would come here.
ये mm like triple M हो जाएगा.
देखते हैं. Right, so this is our 3M. This is the point group C3V. All of them are positive, or all of them negative. So don't need to write positive. Right, can also create C4V. This will be slightly more interesting. Suppose this is my mirror plane. This doesn't have a forward slash sign, by the way, because mirror plane is in the same direction as the principal axis of rotation. So if this is my mirror plane, I get this. Here, I get this. This will give me this. This will give me this. So have I generated a new mirror plane? This one. Is there another mirror plane that I have generated? Generated this. Like generated this. Right, so this is given the symbol M.
तो 3 के लिए क्यों नहीं हो सकता? 3 पे भी अगर हम वर्टिकल और हॉरिजॉन्टल आगे हम डायगोनल में करें तो वो बन जाता है।
नहीं तो फिर अगर मैं यहाँ बनाऊँ इस टाइप के लिए यहाँ नहीं है ना,
इसको वो
ठीक है नहीं ना,
वो वाला नहीं होगा जो वाइट है
नहीं
राइट?
नहीं इस टाइप इधर आना चाहिए,
अच्छा
जब यू बनाऊँ तो इधर आना चाहिए, ठीक है? So this is 4 mm and it has generated, so there's 1, 2, 4 mirror planes, but the signal is 4 mm and the extra 2 mirror planes are understood in the center. You don't want to put so many m's in the center. So this orientation C4B. So this is number 14. I can also have number 15, which is adding vertical mirror planes over here. So I'm not going to draw this. So this is C4B, or the symbol for this is 6 mm. Okay, so this you can probably do as homework. Another note is we want this to be given as homework. Should be taking notes. So now we have 15 point groups. So we have the cyclic groups. We had the action of a horizontal plane on those groups. Then we had an action on the vertical plane on those groups. The question I want to ask is why don't we have C1B group? Why don't we want to put a vertical plane, mirror plane onto this group? Why can I do that? Why don't we have C1B? Why not C1B? I didn't have C1B. I started out with C2, adding vertical planes to C2. Same thing as what? As? No, it's not the same as C1. It's the same as this 2 bar. A C1B is the same as this 2 bar. Just a mirror plane. Because if I were to add a vertical mirror plane here, right? The only way in which I could add a mirror plane is on this axis. So I'll get this point to be reflected over here. So when I have an object above and an object below a plane, and those two objects are in diameters of one another, it's exactly the same situation as this. So I do not have a C1B. Okay? So why not C1B? We have the date here. The C1B is just the same as 2 bar or M. We do not have a C1B. It's not a distinct point group. It's already covered in the 15 point groups that we discussed. Now what we would like to do is we would like to have additional point groups which are called dihedral point groups. And how do we do that? So let's start off by adding more axes of rotation. So all of these groups so far just had one principal axis of rotation. 2 bar, 3 bar, 4 bar, 6 bar. We can also have roto-inversions, improper groups. For example, one of these groups we've already seen, S1. This in a way is equal to another roto-inversion operation, 2 bar. But we can also have 3 bar. We can also have 4 bar. 6 bar we already have covered, right, over there, group number 9. So we can have 3 bar and 4 bar. 2 new groups, 2 new improper rotation groups. So this is one improper group let's have another group, number 16, which is formed by having a 3-bar operation. 3-bar operation, right? So let's see how this is formed. So I have an object here. I do 3-fold rotation. This object lands here. But I really need to follow this by an inversion about this point. So an inversion of this point lands me here. If this is plus, this becomes minus with a comma. Got it? So if I do, now for this point, if I did a 3-fold rotation, that is a rotation about 120 degrees, I land here, then I do an inversion, I get over here, plus this comma again is now without a comma. This point, when I do 120 degree rotation, followed by inversion of this point, I land here. This point, 120 degree rotation,
इक्वेशन ऑपरेटर हमेशा प्लस को माइनस कर देती है।
हाँ बिल्कुल, it creates a diagonal. So this group is 3-bar. It just has an improper rotation axis in the middle, which can have a symbol, a triangle put inside a square perhaps, to differentiate it from a normal proper 3-fold rotation. So this is 3-bar or symbol S3. I can also have 4-bar. Good. So group number 17 will be 4-bar or symbol S4. 6-bar we've already covered. That's just over there, C3H. 1-bar we've already covered, 2-bar we've already covered. So now we have constructed 17 of the 32-point group. That's quite an amazing feat in my opinion. Okay? And we've done this really systematically. Now things get more interesting when we keep on adding more symmetry elements. And it's humanly possible for me to go up till about group number 27. Then I have to resort to some results or some of the simulations. Got it? We fine so far? So let's look at dihedral groups. So if I were to take some CN group and add to this CN group, where n is 2, 3, 4, 6, and add to this another axis of it already has an n-fold axis rotation, but now I add another n-fold axis rotation that is perpendicular to the origin, that is perpendicular to the principal axis rotation. So I take this Cn, and to this I add another n-fold axis of rotation that is perpendicular to the origin. So let's look at an example. Let's look at group number 18. C2 group over here. Now this is my axis of rotation coming out of the plane. My principal axis of rotation. Now what I would like to do, I would like to add to this another axis of rotation, yet again a 2-fold axis of rotation, but now perpendicular to the origin. What this is going to do is going to rotate around this axis, so everything here comes here. So let me draw this. This is C2. My original axis, 2-fold axis of rotation is here. Now I add another 2-fold axis of rotation. This object, or both of these objects are above, this object ultimately this operation will come down. This operation will also come down. No inherent timers because it's a non-integer equation. Right? So this new axis is called the dihedral axis. Okay, and this group has, if you notice, how many axes of rotation does it have? Does it generate yet another axis of rotation? This automatically becomes the third axis of rotation, of twofold. So just one dihedral axis has created another one. So now I have three mutually perpendicular twofold axes of rotations. And the symbol for this group will be 2. This was just the original, another 2, and 3 2s. And old symbol for this is D2 because it's C2 followed by a dihedral axis. Right? I can do the same thing to C3 and create so I have my C3 looks like this, all positive. This is the three-fold axis of rotation. Now what I want to do is, actually this is always a two-fold axis of rotation. I would like to do a two-fold rotation about this dihedral axis, suppose. So suppose this is a new dihedral axis. All of these are positives per se. This would become negative, negative. This would go here. This would go here. Correct? So now I have this, the symbol for this I will be 3 2. 3 2. E3. This is group number 19. Can you generate B4 please on your notebooks?
So in cases में antennas नहीं है.
Sorry, can you? I was keeping with. Or this new axis is generated. Does it generate another axis of rotation? Yes, it does. What about this axis of rotation? Is it an axis of rotation? No, it's not. It's not an axis of rotation. So the symbol for this is I have 4 axes of rotation and 2 axes of rotation. 4 2 2 D4. Group number 21 will be D6 and the symbol for this is 6 2 2. So these four groups, dihedral groups, are made by adding dihedral axis to CN. But I can also add dihedral axis to C and H, C2H, C3H, C4H, C6H. That I can also do. Correct? So let me exemplify this. So what I'm trying to do now is I'm trying to take C and H and concatenate this with a dihedral axis to create new groups that have the old symbol D and H. So let's look at the simplest example. Let's take C2H. Here I have C2H. This is my C2H, isn't it? C2H over there, or 2/4/n. So there is a two-fold axis of rotation here, and there is a mirror plane already in the plane. This was simply C2H. Now I want to add another two-fold axis of rotation that is dihedral, which is perpendicular to this axis of rotation. So let's suppose that is this dihedral axis that we're looking for. So what would this do? This would take this point over here. Something that is above will come below. This is below will come above. This point will come above with a comma. This point will go below. So this is my D2H and the new symbol. So this is the old symbol, and let's figure out what the new symbol looks like. So the new symbol was 2N. But let's try to simplify, let's try to find mirror planes over here. Can you identify any mirror planes in this new stereogram?
Sir, the top to bottom.
This is a mirror plane
Yes.
because corresponding to this, the two pluses, one is in an environment, the other isn't. This negatives, one is not in an environment, the other is. So this is indeed a mirror plane. What about this? Is this a mirror plane? It is. Plus with a comma. Comma here negative, without comma negative. So this is also a mirror plane. The order you could put a comma here, it doesn't matter. Same thing. Is there yet another mirror plane? Yes, there was an original mirror plane as well. So now there are three mutually intersecting orthogonal mirror planes. So the international notation for this point group is M, M, N. So likewise you can create other point groups. Six bar M2, old symbol D3H, 4 N N N D4H and 6H, right? We have these improper axes. So we have S4 and S3. And we also have S6 that we've already done. So if you look at this S3 and S4, what if they had a dihedral axis over here? We have a dihedral axis here and a dihedral axis over here. So let's look at S3. So now number 26. Let's look at S3 and concatenate this with a dihedral axis. Okay, so let me draw S3 plus comma minus comma. Okay. So this was my original 3-bar. 3-fold axial rotation followed by center of inversion. Now I would like to, this was, remember, a 3-fold improper rotation axis. Now I would like to put a 2-fold rotation about this axis. What this would do, this would land this object here. This object will come here. This object here. This object over here. Correct?
Absolutely.
This object. So originally this was 3-bar. Now the symbol for this is there a middle plane over here? Any middle plane?
Full horizontal.
No. This is the middle plane. So the symbol for this is 3M. And whole rotation D3D. This mirror plane that is formed by the action of a dihedral axis is called a dihedral plane. This is a dihedral plane. Finally, I don't want to belabor this point. Group number 27 would be you take S6 and concatenate this with a dihedral axis. And the symbol for this would turn out as, sorry, you want to do this with a 4. You want to do this with an S4. The symbol for this is 4-bar 2M D4D. Okay, so now we've kind of demarcated 27 point groups. Now all of these point groups have different kinds of symmetry elements, and we lump all those symmetry elements together and form a mathematical group. Now we're left with 5 point groups. Okay? So we had cyclic groups, we have inversion groups, we have roto-inversion groups, we have horizontal planes, we have vertical planes, we have dihedral groups of different kinds. Now we left with 5 groups, and those 5 groups generally they are called cubic groups. And they are the most common and easier, most difficult to understand because the number of symmetry elements in those groups is very large. So let me, and it's important to visualize them on a computer or through some visualization methodology, but let me state what those groups are. So group 28, 29, 30, 31, 32, these are 5 groups. T, PD, TH, these are called the tetrahedral groups. O and OH, these are called octahedral groups. And these are 5 cubic groups. And they have different number of symmetry elements. OH is the point group that has the highest number of symmetry elements. In fact, it has 48 symmetry elements inside that group, in the structure of that group. By the way, each group satisfies all the properties of a mathematical group, closure, and so on. So if I look at the tetrahedral group, the commonality of all of these groups is that they have a threefold axis of rotation along the body diagonal. Threefold axis of rotation along the body diagonal. So if you take a cube, and you look at the body diagonals of this group, of this cube. So here is one body diagonal. This will be a threefold axis of rotation. So you take this axis and rotate this cube by 120 degrees. You get back exactly the same cube. Okay. So likewise, this axis here is going to be a threefold axis of rotation. This axis here is going to be a threefold axis of rotation. And this axis here is going to be a threefold. So there are 4 threefold axes of rotations in this group. And then you successively keep on adding more symmetry elements, you get higher and higher symmetry inside this crystal glass. So T has these 4 threefold axes. T also has 4 3-bar axes. So each of these axes is also a 3-bar axis. So you rotate by 120 degrees and then do an inversion axis. Of course, this also has the identity symmetry element. Additionally, the group P also has 2-fold axes along the edges. So these 3 edges, the T group has 3 2-fold axes, each one along the edges of the face. So group T has all of these 12 elements. And the symbol for T, the new symbol for T is 2, 3. This is 2, 3. Identified by 2-fold axis 2 and a 3-fold axis along the body diagonal. Now if you add mirror planes to this, a mirror plane in the center of the cube, horizontal, vertical, from back to front. If you add these 3 mirror planes, you get the TH group. Right? So to these mirror elements, to these symmetry elements, you add 3 mirror planes. You get the TH group. The TH group has a symbol M3. So let me just try to draw. So we have 15 minutes for the next class. So let me try to draw these mirror planes. You take everything inside this group, in the T group, and add 3 mirror planes. Let me attempt to do that. So one of the mirror planes will look like this. Another mirror plane might look like this. And yet a third mirror plane will look like this. So this group PH is made by taking T and adding 3 mirror planes to it. Okay? This group PD is made by taking diagonal mirror planes. And there are 6 kinds of diagonal mirror planes inside a cube. So this group is also made from T, and the symbol for this is 4 bar 3N. And the nice thing about this is that it also has a 4-fold axis of rotation along the body, along the edge of the face. O likewise is 4-3-2. It also has 2-fold axis of rotation along the face diagonals. Okay, so 4-3-2 has a 4-fold axis of rotation, 3-fold axis of rotation along the body diagonal. Whenever there is a 3-fold axis of rotation, remember there is always a 3-bar axis of rotation as well. Additionally, along the face diagonals, it has 2-fold axis of rotation on this face diagonal, along this face diagonal. This will qualify this as an octametry cubic group. And if you add these mirror planes, these 3 mirror planes to O, to get OH group, which has a symbol N3N. Okay. Notice that in all 5 of these cubic point groups, there is this number 3 in the middle. Number 3 at position number 2, which represents a 3-fold axis of rotation along the body diagonal. Okay, so this is a quick check to see whether that point group belongs to the cubic class or not. Okay, so these are our 32 point groups. Now, the role of these point groups is that every macroscopic property of a crystal depends upon which point group does that crystal belong. Number 1. Number 2, the outward appearance of crystals put that crystal in a particular point. The point group determines what the external morphology of a crystal looks like. Because the external morphology, for external morphology, you need to know what point operations would leave that crystal invariant. So you look at the geometric center of that crystal and do a class of symmetry operations, point symmetry operations, and one, you will find out that the crystal belongs to one of these 32 point groups. Okay. We've also seen that these symmetry operations are, all of them are point operations, and some of these 32 point groups have 2-fold axis of rotation. Some of them have 4-fold axis of rotation. Some of them have just 1 or 1 bar. Some of them have mirror planes. Some of them have 3-fold, 6-fold axis of rotation. So now we can break up these 32, in fact simplify these 32 point groups and lump together certain point groups which have commonality. For example, all the point groups that have a 4-fold axis of rotation or a 4-bar axis of rotation, they can be lumped together in one set. That will be that set will give you a crystal class. That is a tetragonal crystal system. All these point groups that have a 3-fold axis of rotation along the body diagonal will belong to the cubic crystal system. All of those that have a 2-fold axis of rotation will belong to the monoclinic. All of those that have a 6-fold axis of rotation will belong to the hexagonal. All of those with a 3-fold or 3-fold axis of rotation will belong to the triclinic. Will belong to the, I don't know, rhombohedral. All of those that just have 1 or 1 bar will be triclinic. So you can get 7 crystal systems out of these 32 point groups. And it's easier to identify crystalline structures and lattices based upon those crystal systems. Every crystal will belong to one of 7 systems: cubic, tetragonal, orthorhombic, monoclinic, trigonal, rhombohedral, hexagonal. And the nice thing is that if you put these point groups together and combine all these symmetry elements, it puts constraints on what the shape of the unit cell looks like. Okay, so everything is now transformed from a mathematical group theoretic symmetry operation approach to just looking at the shape of the unit cell. So the next class we're going to see how the crystal systems, the 7 crystal systems, emerge out of these 32 point groups. So that we classify all these crystalline solids into one of the 7 crystal systems. And for that we only have to look at the shape of the unit cell. The unit cell is a replicated unit inside the lattice. You have one unit cell, you know what the entire lattice is going to look like. Just repeat it by translations. And then you put face-centered those different faces inside those 7 crystal systems to get the 14 Bravais lattices. Okay, so this is the entire glory of crystalline structure coming in front of you. Okay, so in the next lecture we're going to look at the 7 crystal systems and how they come out from the point of view.